Before we dive into 1-3, which is limits at infinity, I wanted to take one last look at the composite functions with limits. So, meaning the ones that, and there's an example right there, but the ones like the x approaches 3 of f of g of x, or the limit as x approaches -2 of h of 3x to the fourth minus 5. So when you've got that nested function within. So here you've got a visual of the limit as x approaches 0 of f of x. So as you would typically do, we're going to work inside out. We're going to work inside out, meaning let's just focus first on this f of x. So the question becomes, what's the limit, if it exists, as x approaches 0 of that highlighted blue f of x? And if we look at the graph of f, we can identify that that limit is 2. Right? We can see as I'm approaching from both sides, that height is trying to approach 2. More specifically, though, we notice with this graph that that limit is going to approach 2, but it's only approaching 2 from the left. Meaning, if I'm looking at all of these values as I'm getting closer and closer to 0, to my x value of 0, my y values are 1.9, 1.99, 1.999. If that makes sense. We don't get a scenario where it's 1.99 from one side and 2.001 from the other. So I'm going to make a note, if this is clear to you, that what's inside that blue highlighted piece is actually approaching 2 from the left. Why is that relevant here? Because now, if I'm looking at the next piece, I know this is 2 from the left, so now the question is, so the limit as x approaches now 2 from the left for, and now I'm on the outermost function, 2 from the left of now this f, we'd see that that would be, let's see, 2 from the left is taking us here. So we know that that would approach 0. There is no reason for us to look at this side of the graph because this value right here doesn't get larger than 2. It's always smaller than 2. So this would give us a solution of 0. So our answer to this, just so that I'm clear, is at this limit. So let's look at these two examples. So this is same idea. So my graph of f is on the left, g is on the right. Question 1 is asking, what's that limit as x approaches 5 of g of f of x? So I'm going to focus first on the nested function and identify what's my limit as x approaches 5 just of f. And if I'm looking here, I can see that as I'm approaching 5 from both sides, my y values are reaching 1, but they're always a little bit smaller than 1, right? So our answer, similar to what we just did before, would be they're approaching 1. And to be more specific, 1 from the left, because wait, there's more. So now we're going to take that value that we just got, 1 from the left, and see phase 2. Now what's going on with my outermost function as x approaches 1 from the left of my g? And if I see here, as I'm approaching 1 from the left, I can see that, oh no, I can see that my graph is approaching 1. And again, mindful of the fact that we don't care what's going on to the right of 1 because our graph for f approaches 1 from the bottom direction. So it's always less than 1. Now, if we look at the second problem, that says the limit as x approaches -2. -2 from the left of now g of f of x. So you'll kind of see this pattern now. So I'm going to look to see what is the limit as x approaches -2 first of f of x. And I'm going to go back to my f graph and look as I'm approaching -2 from the left. Looks like those values are approaching 1. Looks like those values are approaching 1. From what direction? It's from above, right? So this would be, if it's relevant, we're going to say 1 and from the right because it looks like all those values are 1.1, 1.01. And so then our next step is then seeing, now what about that outermost function as our x now approaches 1 from the right? And as I'm approaching 1 from the right, I think we're seeing it, that would approach -5. So in 1.3, we are working with limits at infinity, which is a question of saying, what's going on with my graph as my x's approach infinity or negative infinity? You'll see on this slide as well, just a refresher of what you did when you worked through end behavior with even and odd powered polynomial functions. You identified the degree and if it's even or odd, and then you focused on the leading coefficient and whether or not it was positive or negative. Those rules are going to be useful in just making some of the practice problems go a lot faster. So let me know if that looks completely new to you. I don't think so, but we can always work on it. But let's see what that looks like here. So this is just sort of a warm-up problem where it's asking us what's the end behavior of this function f of x. This is another way of saying we're talking end behavior. We're now using this notation, right? We're saying what's the limit as your x approaches infinity for this function, and then what's the limit as x approaches negative infinity. So I hope you're comfortable in seeing as your x's get really large, we can see what that pattern is for our y's. Our y's are getting large as well. So it's approaching infinity. And then I would say the same sort of situation as my x's approach negative infinity, my y's are approaching negative infinity as well. So sometimes your graphs increase or decrease without bound. Here, though, if they're asking us, well, what's the limit of this function f of x as your x approaches infinity? And we typically see this, but we can identify as well clearly the behavior of this graph. And we notice that this is approaching 3. So in this example, my limit as my x approaches infinity is 3. And you can tie that in and see how that relates to what you used to do with horizontal asymptotes. Because we know horizontal asymptotes is just saying as my x's get really big or as my x's get really small, if my y's start to approach a finite value, like y equals 3, then I would say that equation, y equals 3, is a horizontal asymptote. I want us to be mindful of the fact that it could be a one-sided asymptote. Like in this example right here, I can see that the limit, I'll use this, as my x is approaching negative infinity for this graph p of x, is going to equal 0. It's going to equal 0. And I can just say then that y equals 0 is in fact a horizontal asymptote for that particular function p of x. So just to be clear, it doesn't have to approach from both sides, from infinity and from negative infinity. Okay, so I'm gonna pause this here and have you all work through some of these problems. I think these are pretty decent warm-ups and a little refresher from the earlier units, and then I'll post what the solutions are. So this is what our solution should look like for this example. And we're going to be more specific now about the notation
And when we use equals, I'm a little loose with it, but I want to be better. When we use equals versus when we use like an arrow that demonstrates approaches. And then the DNE is just no, right? There's no equal, there's no approaching. All right, so now let's do a little refresher on what we know or remember about horizontal asymptotes, particularly when it comes to our rational functions as well as some of our polynomial functions. All right, so here's our question. How did we learn back in the day how to find the horizontal asymptotes, particularly for rational functions? So what I have here are three different scenarios, and I say rational functions, but we could be working with functions where we're just going to look at degrees, and they might have radicals in them. It doesn't matter. We're just going to be looking at the highest power for these. So there are three conditions that can take place. Let's look at this first one, and that's when, oops, oh, that didn't, sorry. That's when our function is top heavy. So that just means when the degree in the numerator is larger than that in the denominator. So if I looked at this first example, g, I can see that the numerator highest power is 6. So is degree 6, denominator is degree 2. And if that's the case, then it should make sense to us that the numerator is going to hit those bigger values faster than the denominator, which means our graph of g is going to either increase or decrease without bound. It's going to get bigger faster. So this is our result, that the limit as x approaches infinity or negative infinity. I just didn't write that down. So that limit of g of x is going to approach either positive or negative infinity. We'll do a couple of examples and we'll be able to sort of tweak out which one it's actually approaching. All right, so that's condition one. That's when it's top heavy. Top heavy implies there's no horizontal asymptote because those y values are going to get big fast or small fast. All right, second condition. That's balanced, and that's when your degrees in the numerator and denominator are the same. So if we looked at this h of x, the highest degree on the top is 7. Highest degree on the bottom, and I intentionally sort of flipped it so that you're not comfortable with the fact that your highest degree is always the first one. So here, that highest degree is actually 7 as well. And when we have that balance, what we end up doing for the horizontal asymptotes, so we're going to be doing this for the limits at infinity, is we take the ratio of the leading coefficients. So leading coefficient for the top is 4. For the bottom is negative 13. And so we could then write, now I'm here, that that limit as x approaches infinity or negative infinity for h of x is negative 4/13. And we'll do an example where we sort of play around with some ratios as well. Figure that out. And then there's this third scenario, and that's when it's bottom heavy, when the degree in the denominator is larger than that in the numerator. So for k of x, the degree up top is 5, on the bottom is 6. And so again, thinking about it, that means when my x approaches infinity, my denominator is going to get larger faster, and it's going to get significantly larger. And so if something in fraction wise, I have a big number on the bottom, that's going to approach 0. So with respect to the horizontal asymptotes, we know that that's y equals 0. So I know that my limit as x approaches infinity or negative infinity for that function is going to equal 0. So the first couple of problems I think we can do fairly quickly. This is just asking for our end behavior. The limit as x approaches infinity of, and question 1 is a quadratic, right? And this is still helpful in our even and odd functions because it's a quadratic, which means it's even. It's got a leading coefficient of 3, so I know that the behavior looks like this. And so my limit as x approaches infinity for this is going to approach infinity. Great. So for 2, I have an odd function with a negative leading coefficient. And so for that case, I know that my behavior looks like so. Negative leading coefficient, odd function. So the limit as x approaches negative infinity is actually going to approach infinity. Now let's look at a couple of different ways. The first thing I want you to identify is one, it's asking for the limit as x approaches infinity. Two, we're looking at the highest degrees for the top and bottom, and we can see that both of them are degree 2. It's balanced, which tells us it's going to be the ratio of the leading coefficients. Now I'm going to give you a way too if you're just not comfortable with that approach. If you're comfortable, totally ignore me. Okay, so we could rewrite this problem by dividing everything through by the highest power of that function altogether, so that it looks like this. Why would I do that? Well, it's because if I take this, and I hope you're okay with identifying why we're allowed to do that. You just take the same number or the same expression, 1 over x squared, and you multiply everything through by that to the top and the bottom. And if we do that, it leaves us with this if I clean it up, both in the numerator and the denominator. That's helpful because if we look at each term individually and we see the limit as x approaches infinity of negative 6 over x, I know that the bigger my x gets, negative 6/10, negative 6/100, so negative 6,000, that's going to approach 0. And if I did the same thing to the second or the third term in the numerator, that would also approach 0. And then if I looked at the last, the minus 1 over x squared in the denominator, and I could see that would leave us with negative 3/2, which is the same as what we got in problem 3. All right, so let's keep going. So let's look at question 4. I want us to start being comfortable with just focusing on the what we refer to as the dominant terms, the highest powers for both the top and the bottom. So here, I'm looking at the limit as x approaches infinity of like this ratio, but as your x gets bigger and bigger, what I have circled, that's my dominant term, right? Because that minus 2 is going to be chump change once my x is at 100,000. And the same goes for in the denominator, the 2x and the 2. When your x is 800,000, when you cube that, that is significantly more powerful than multiplying that number by 2 and then adding 2 to it. So that is all that to say that is, when I simplify it, 3 over 4x squared. And I know as your x approaches infinity, this is going to approach 0. I can also jump straight to the fact that I know it's bottom heavy, so this is going to happen. And that explanation is why. So I know that my limit as my x approaches infinity for that is going to approach 0. Now, in keeping with that same idea, that's going to help us with question 5. The limit as x approaches infinity of this expression. Now, again, as my x grows and grows, these two are the dominant terms in that expression. These two are the dominant terms, which means this is going to take on the appearance of this business, 2x to the 4th over 6x, which I can then clean up. 2 over 6 is 1 over 3. And then I've got x to the 4th over x. So it's actually x cubed. So this is x cubed over 3. X cubed over 3. So that simplifies to x cubed over 3. And I know that's an odd powered function, positive leading coefficient, and my end behavior for those functions looks like this. And so I know that this limit will approach infinity. Nice. So this same idea, except this one's super clean. I can simplify that to 3x cubed, and my limit as x approaches negative infinity This is still the same end behavior, positive leading coefficient, odd. So this will approach negative infinity. So here are a couple of other examples. And you'll see they're similar to what we did, except in question 7, you'll notice that the numerator is in factored form. So if I wanted to see what that dominant term is, like what is my highest degree in the numerator, I would have to expand that out just to see what's going on. So the highest degree that that top would take on is if I took the product of all of the highest terms in each sort of separate factor, which means I'm going to have to look at 8 times n times 2n, right? And we don't want to go through the process of FOILing or distributing this all out because that's a waste of our time. I just want what's that highest power? What is my leading coefficient of that highest power? And so 8 times n times 2n. So the numerator has that dominant term of 16n squared. And the denominator looks like it's 4 over n squared. Yes, that's right. So I can see that it's balanced, which would leave us with 4. Now, before we dive into 8 and 9, which look a little bit different because those aren't rational functions, but we're still going to approach them in the same way. But here is one thing, and it's algebra 1 related. Make this a little tinier. And it's the square root of x squared. What is the square root of x squared? So it's not x, but it's the absolute value of x. Quick refresher. Here's event 1. What if x were 3? Then I would say the square root of 3 squared, well, 3 squared is 9, and the square root of 9 is 3. So that checks out. That's great. But scenario number 2 is what if x were negative 3? Then I would be taking the square root of negative 3 squared, which is still 9, which is then 3. So we could say that the square root of negative 3 squared would just be the absolute value of negative 3, which leaves us with 3. So let's remember this as we proceed. So if we're looking at 8, I am still going to focus on the dominant terms for this problem. I'm still going to focus on the dominant terms for this problem. And those would be these two right here. So I'm looking at the limit as my x approaches infinity of the square root of x squared over 3x, which then takes us to the top would simplify to the absolute value of x, and then the bottom to 3x. And just because I can, I'm going to write that as this. Now, let's remember what that graph looks like. So I have it right here. And so we know that if I have the absolute value of x over x, my graph looks like this. Now they're asking us to find the limit as x approaches infinity. So I know as my x's continue to get bigger without bound, what's my y approaching? Sure is, my y is approaching 1. So that leaves us with 1/3 times 1, which is 1/3. That's great. But let's look at 9. So you'll notice 9 is the same function, but in this case, we're asked to find the limit as x approaches negative infinity. So I don't have to do that work again because I already did it for problem 8. I'm still on this right here. So now our charge is, well, what's going on as our x is approaching negative infinity of 1/3 times absolute value of x over x. So now I think we're going in this direction. And I know as x approaches negative infinity, that ratio approaches -1. So that leaves us with a limit of -1. Let's look at this problem last. So here we've got an example where they're asking us to take the limit as x approaches infinity. My suggestion would be for this, because these are now working with these exponents, I would, for this particular problem, rewrite it so that it is clearer without the negatives. So maybe let's rewrite the e to the negative x as 1 over e to the x. And let's rewrite the denominator the same way. And we're taking the limit as x approaches infinity. Okay, now by doing that, we have hopefully worked out visually that this and this term, they're going to approach 0, because if I plug in, as my x's get really big, 1 over e raised to a big number gets close to 0 pretty quickly. So then that leaves us with these two terms, and you'll notice I can simplify 3e to the x over e to the x to just 3, because those two cancel out. And so my limit is going to be 3. So what if we took this and now we were asked, what about as x approaches negative infinity? So it is the same idea, but maybe what we can do is let's define this value b, because plugging in infinity into an expression or negative infinity is just weird. So what we can do instead is we can say, let's let this value b approach infinity. And that way our negative b is approaching negative infinity. So in this case, I'm thinking of it, tell me if this makes sense. So I'm going to plug in negative b into this expression just to see what does that approach, because right at that my negative b sort of represents the negative infinity. So if I were to plug in this number that is approaching negative infinity, it would look like this. So 3e to the negative b minus e to the negative b, so that's e to the b, over e to the negative b plus e to the b. And so by doing that, now the question becomes, let's see which of these approaches 0, and let's see which of these becomes sort of the aggressor in that expression. So we're left now with 3 over e to the b minus e to the b, because we've gotten rid of, or we are, well, that's a 1. We are getting rid of all of our negative exponents, and then plus e to the b. So now it's these two terms, right, that are going to approach 0, leaving us with this expression. And you'll notice here that I can simplify this. I've got an e to the b and an e to the b here, except let's not lose our signs. So that's negative 1 over 1. So actually, this limit, as x approaches negative infinity, is negative 1